Welcome to Silicon Valley Big Data Science. It's a beautiful evening. Really appreciate you guys taking the time to come and spend your evening with us. Drinks and pizzas are gone. It's good. We always have a prediction how many pizzas to order, and it seems like this time we were behind. Probably accurate. How many of you are here for the first time? Awesome. This has been a wow. This has been consistently true for the last 3 meetups. We have 80% of you lifting. That's the first time you're here. There's several ways to think about our product and company, and you'll see a very intense, focused discussion around deep learning. I think playing this video might give a quick understanding for people who are looking for this.
So your business has massive amounts of customer data stored in Hadoop that you need to analyze. The more data you analyze, the better you can predict how to serve your customers. But organizing and analyzing this data requires complicated math, and modeling this data to come up with better predictions usually takes days to weeks and is often error-prone. So, what's the best solution? Quite frankly, it's H2O from OX Data, the industry's first open-source prediction and math engine that will enable you to make better predictions and build accurate models faster. And as makers of the parallelized modeling and scoring engine of Hadoop, we got you covered. Here's a real-world example. Let's say your business is trying to understand the best product placement for optimal customer engagement. So you want to model the interactions of your customers on your website to make better predictions on what they want to do next. Well, H2O allows you to model all of your data with better algorithms using mini machines. This way you won't have to sample a smaller data set for performance reasons. H2O then allows you to score hundreds of models in nanoseconds and deliver better predictions to your business. The reality is, data is messy, and so many hours of data science go into moving big files and munging missing features. And that's why we designed H2O's data console to make those tasks a piece of cake within a familiar interface. Simply put, H2O makes big data science, well, simple. So when you're ready to mine the true gold hidden within your big data, you're ready for H2O.
Sometimes you have to stop and say, Elvis is in the house. Sequent, Nahum just arrived. He's one of our biggest customer evangelists. So, Nahum is in the house. It's actually quite a august audience. We have Hassan, who's also been using our product for a while. Share this. He's the data scientist who matters at Share This, which has a pretty dramatic data set, which is massive connected data set across the world, sort of the whole web. We are actually at one of our first customers. This is Vendavo, which is where we cut our first teeth, if you will. So pricing engine, they're building a great pricing engine, which is in the cloud, and they're using H2O to do their math behind it. This is the team. The other reason we are here is because of this team. It's growing. We were 2 lines, now 4, and slowly getting to 20, 25. So we continue to grow. We have a phenomenal, robust customer base and very avid user base. We had about 100 users in January, and we are about 4,500 users as of today. So it's growing rapidly, essentially. The growth curve is 25% week on week. So it's pretty, and we spend, our first marketing person, purebred marketing person, is Joel, who just joined us. And other than Joel, Josephine, Max, and today Kendall, most of our team is engineering, and so we're busy building product. Our product, well, our team is not complete, story of team is not complete without talking about phenomenal advisors that surround the company: Stephen Boyd, Rob Tibshirani, Trevor Hasty. who've basically the elements of statistical learning books, books we read, books I read to build algorithms or use algorithms in R. Right? So one of the other aspects you'll see of the product is it's a R, it connects into R, so you can actually use it like you'd use in an R package. Finally, our customers, we've had early partnership with Netflix and Nahum, PayPal, or Vendavo. So our customers drive our roadmap and have been very good partners in what we built here. So with that, I want to quickly bring this event into perspective. This is one of 90 events we've done in the last year and a half. In the audience is actually someone who hosted us for the first time, our first meetup in March, and that's Stephanie. She put us up in our first ever meetup, so she's here on the latest one, so which is probably good. She'll probably see the growth. But our product was taken to the market through complete word of mouth, mostly word of mouth. So if you're here, download the product, use the product, give us feedback, tell others to come. So we'll be able to take it to further. So that's what I had on my list of things to talk about. Deep learning through examples. This is the second in a series of talks that are likely to come. We have the first one was September 3rd. How many of you attended the last talk? Of course, now we remember her. Perfect. So there's some advancements from last week. The product continues to get better. There is on the leaderboard. Do you have the slide for that? Yeah. We actually after the talk, one of our users got inspired and he took it to Kaggle. So it is part of, it's on actually leading on a Kaggle contest at the moment. And we expect a lot more of those to happen. So use the product, play with it, pick a data set, pick your favorite data set on Kaggle, and roll forward with it and give us feedback. You're here too. Arno himself is intending to join the Kaggle contest and see what happens. So we'll see the man versus Superman will start. With that, I think you actually have a slide talking about yourself. But at the heart of when Arno was actually talking to us on a weekend, and there was one day where I actually did say I had a customer lunch, and I did not go to that customer lunch because Arno was really like one of the first physicists who was capable of hacking great code, and he's done good stuff before, Slack, and a couple of years at Skytree where he built most of the core libraries there as well. But he was the perfect fit from a culture standpoint. He wanted to teach as a physicist, he wanted to take what you invented to the world. So I think it's a match made in heaven. So since then he's been all over the planet at the moment in terms of fame as well as quite well-deserved fame, because he's been hacking as well relentlessly. If you pull up the GitHub, actually, go to our GitHub if you want to know about our company or about this product. The true source is the source. So read the flaming source, as Linus told. This is about 14,500 commits, 37 contributors over the last year and a half. Right, so it's one of the fastest. If you think about in perspective, Cassandra, which is another popular, highly successful project, it's about 14,000 commits, 37 contributors, but over 5 years, right? Includes the Facebook commits and stuff. So it's a pretty fast-moving project. So one of the things Arno said himself was to get to the top of the commits list in 9 months, and he's probably hit that. So it'll be fun. So yeah, so keep the questions coming during the talk. So hopefully there'll be fun Q&A session before and after. But we are really excited, and I have complete pleasure in bringing Arno explain the labor of his 9 months of love.
Right.
Deep
Thanks,
learning.
Sri. Thank you all for joining tonight. Who has seen my last talk last week? Just about a handful of people, so there will be a little update. So as promised, there's more. So yeah, my background is supercomputing, C++ mostly, and now Java, machine learning, simulations, millions of core hours on supercomputers, the biggest supercomputers in the world. We had access to at SLAC, the Stanford Linear Accelerator Center, where we modeled physics, particle accelerators, electromagnetic simulations on 10,000 cores, for example. And then I was named a Big Data All-Star. That was a nice surprise. So now this is what's happening just right now, today. The Africa Soil Property Prediction Challenge is a Kaggle challenge. You know Kaggle, right? Who knows Kaggle? Everybody? #1 ranking right now is our friend Joe, who uses H2O deep learning. From R, he scripts it and he runs it overnight on a single server, and he has the best prediction of 413 teams. And actually I joined yesterday, or the day before yesterday, and I'm already up there. I used to be 11th, now I'm 17th, so I guess I gotta step it up a little. Clearly the tool is able to perform well, right? This is a pretty remarkable achievement. And he's saying he can do more. So he literally wrote this text there to us in an email today saying, I'm sure I can do more. And there's 40 days left, so it's not like it just started and we're the only ones submitting anything. This has been going on for a while. Sorry, can somebody turn the volume down just a little bit, please? It's on the right side in the back. It says volume, master volume, on the speaker itself. So this talk will introduce H2O. And I'll show you a brief live demo so you see the product in action, and then I'll show you the methods behind deep learning. And after that, we'll get more into hands-on demos, real data sets, how this actually works. So Shri introduced you to the product. These are the books. Maybe you remember the books, but not the names. These are the main machine learning textbooks that students read all over the world, and these professors, they show up at our door sometimes unexpectedly just to say hi and to discuss stuff, GLM. So, for example, Stephen Boyd here, he just shows up and talks to Tomasz and others to say, let's figure out something to improve this method. So these methods that they know, we know as well. Right? It's not some like 10-year-old method that's implemented. This is leading edge. And if you want to click on that code mesh talk out there by Cliff, then you'll see why he's the CTO here at Hexadata. It's because he wrote the Hotspot Java compiler. He knows how to make Java fast. He was one of the people who made Java fast so that it can be used as a machine learning platform nowadays. It's not just something that's slow. It's only slow if you allocate a lot of objects and delete them all the time, or let just Java handle it, clean up after you, but we don't do that. We allocate long arrays. It's also the #1 machine learning platform on GitHub for Java, which is an important thing because Java is the #1 programming language in the world. So anybody who can program anything, there's chances it's Java, and then they want to do machine learning, so those two go well together. What do you want if you're a customer? You want it to be fast, right? You want it to be in memory. That's what it means to be fast these days. Until we have faster memristor-based memories or something that go over terabytes and exabytes and whatever. Right now it's main memory, DRAM, distributed. That's always going to be true going forward. You will not have one machine that's just good enough. There can always be another machine somewhere. So you want more data to fit onto your system, and that system is distributed, so you can handle all the data, not just a sample. And then, of course, you want to know what you're doing. You don't want to get a black box that you don't understand, and somehow there's a magic trick inside that you can change a little bit for your needs. So open source is important to us, and the extensibility comes from the API and the SDK. So all of you will be able to program in H2O. All you have to do is download it and try it, and we are here to help you. So this is not a secret or anything. This is all open and supposed to be used either for Kaggle context or for further development to do your own stuff. And of course, H2O was developed from scratch to meet all these requirements. So H2O can be on top of HDFS. You can also just download a file from Excel or from your laptop's browser or text, whatever the finder, your file system. But usually it's HDFS, right? Customers have data, and data today is in HDFS because it's a lot of data. They don't know what it is, where it is. Just dump it all there and then suck it in later. So H2O can suck it in no matter whether it's on the same cluster or somewhere else. Of course, you just talk to the HDFS server and say, give me data. If it's the same co-located cluster, of course, it's better. You can run it MapReduce v1 as our job that's launched by the MapReduce, but it's not really a MapReduce, a Hadoop MapReduce job. It's its own Java MapReduce that we wrote. So there's no slowness going on with shuffle and all that, and to disk and all that kind of stuff. We don't do that. And of course, Yarn makes it better for resource scheduling, so there will be upcoming news. Of course, Yarn is going live everywhere slowly but surely, and H2O will also be launched by Yarn, not surprisingly. Now, the key here is really that there's an R API as well as Java, of course, and R talks to the actual H2O server via JSON. It actually sends a command over and says, hey, please execute this, or please do this. R, when we launch R, we don't launch it on the server, on the cluster. We just launch it on the laptop. The only thing that runs R is my laptop. And then I say, hey, H2O cluster, please load a terabyte from HDFS. And that terabyte gets sucked in on that cluster. And then I can say, OK, process it. Give me a summary, run k-means, run deep learning. Whatever you're doing is not in R, but it's from R. So you can program it in R. You can do your cross-validation logic. You can do your train, test, prediction, whatever you want to do. Your number crunching happens on the cluster. But your final scores for a comparison, for example, how well did this holdout set do? That one number you can send back to your R instance, right? And you can then make decisions from your R script to steer the cluster. So that's the whole key here, that you're not sending R to the worker nodes and say execute R code, but we're executing Java code that's distributed. So what is H2O really? Well, it's really just a jar file that you launch with java-jar h2o.jar. That's it. And this one jar file contains a web browser, actually a web server, I should say, that you can then talk to and look at it, and you suddenly see a web page. It also contains a distributed in-memory key value store. That's the secret, basically. That's what's inside H2O. Everything that you put in there, every machine learning model, every data set, everything that you put in is put in as something under a key. And there's many things that you put in there, and they all have a key. And those things are just bits. You just put in bits. And we know what they are. We compress numbers. So if you give me 1 billion numbers, I'll look at them and I'll say, OK, they actually, let me look at 1 megabyte at a time. Let me look at them, and they all look kind of similar. They're all in the range from 5 billion to 7 billion, those integers. So all I need is about 1 billion, which, oh yeah, fits in 32 bits. So I'll take a 32-bit representation and store the actual integers that I need to get into that number space into floats, right? Those are 32 bits. And then that's how I get my columnar compression, because each column has different data types. Some are just ones and zeros, some are long, some are double, some are short, small little numbers. Sometimes you only need 1 byte, sometimes you need 2 bytes. So each megabyte, roughly speaking, of the data set gets cut up and looked at and then compressed. And that gets put into the KV store under the key. So in the end, you have maybe 10,000 keys for a 100 gigabyte data set. And those are the only objects that you have to allocate, so to speak. Those are long arrays of elementary types, like a float or double, or a byte array in our case, right? And those byte arrays will not be touched. They won't be cleaned up by the memory, garbage collection, nothing. They're just there. And you just read, and maybe you write to them. But you write in place in those arrays. You don't reallocate anything. That's why Java is fast, because you don't do what Java lets you do if you don't know what you're doing. So then when you have these numbers in there, then you run some MapReduce logical algorithms on top. And our MapReduce is different from the Hadoop MapReduce because it doesn't say everybody does this, and now you reduce it to one guy via disk. Or then you have to shuffle and figure out who needs what from whom. No, what we do is we run many, many little maps. Each thread runs a different map. Then as soon as they're done, they aggregate their results in a reduce step, a small, fine-grained MapReduce that all these threads already accumulate their results. So there's only a few selected network traffics hops needed, basically, for the actual reduce in the end, because most of it happens intra-node on the same node by these different worker threads. So once you have all this in place, you can, of course, then run k-means, which is just a MapReduce, for example, or deep learning, which is also a MapReduce, or random forest, which also uses MapReduce. So we write our algorithms to use MapReduce paradigm and to actually get stuff done using these elementary building blocks. And you can do the same. You can just say, okay, let me look at the k-means code and change it, because I need to do a SVM or something. It's not that difficult, right? You don't need to change this store that's distributed and the non-blocking hash map and all this kind of stuff. You don't need to know about that. So once you have that in place, now you can use it to do scoring. You can do that from R. You can do it in nanoseconds. When we say nanoseconds, we really mean nanoseconds because our methods export their final model into plain Java code. So if you have a decision tree, then that will actually say, if my number is greater than 5, and this number is less than 7, then I'm a buyer. And those comparisons are hard-coded in the Java code. There is no heap lookup of some object somewhere in memory. No, it's in the code is right there. It's plain text Java code that we export. And you can put that into your production engine through Storm or something, and real time, it's as fast as it gets, right? It's all L1 cache, just register-wise comparison. All right. So soon, I think this coming week, there will be a meetup about this. That is Spark and H2O together. Spark is a nice platform to do data munching, right? You can SQL queries and stuff, and you have memory, and you have these RDDs that are not mutable. They're just there. Your data is still there, but now it's in RAM instead of on drives, hard drives. So now it's faster. Your data comes in faster. You can munch it faster, but then you still need to do machine learning. And you can do the machine learning with H2O on top of Spark by using sparkling water, which is in the making right now. You can read that blog. You get the slides. You can click on all these links. It's all linked.
Do you use Spark's MapReduce, or do you use your custom MapReduce for
You would use ours for the machine learning part, but theirs for the munching part, right? If you do like an SQL query first, then you would create an RDD with the Spark MapReduce that contains the SQL answer, so to speak. And that answer then gets sucked into H2O in the same JVM without any overhead other than one copy. And now it's mutable. H2O can change the data. It's not just a read-only thing anymore. Now it suddenly becomes a playground for those machine learning algorithms. So you have to show up here if you're interested about the combination of Spark and H2O. Our colleagues who are working on that will present much more than I can know. But this is just a code example that I got last week.
Is this can we write code in R or Scala Python?
I would think that you can still write code in R once you have the RDD ready, right? The RDD from the Spark side is ready. You can just write H2O code in R to load it. I'm not sure how much we can remote control Spark with R, but whatever is possible, I mean, they have something that in that respect as well. So yes, definitely for R, you want to use H2O. That's the native combination. Especially since John Chambers, who wrote S, and is also an R committee member, he said H2O is one of the 3 possible promising future projects of R. So that's where it's heading. We are in CRAN. Definitely H2O and R go well together. I'll show you a live example of this, but you can just see the stuff you can do in R. Who uses R here? About half. Who does not have any idea what R is or how it works? About a few. Okay. So R is not quite a programming language, but pretty close. It's a statistical toolkit that does all these things like mean, sums, and correlations, and holdout set generation, all that. But all of that stuff is usually done on a single node. And now you can use it on a distributed system to do all the same stuff on big data through H2O. But we have to write a code. And when you write H2O.deeplearning, then this is actually our deep learning that's running in Java, right? No more R. It just looks like R. But this module that you load in the beginning that says library H2O, that actually says, I'm putting in a hook. When you type H2O.deeplearning, I'm going to send this JSON request to the server and say, please run deep learning, right? R is just waiting for the response to come back. All right, back to physics. Took me a while. All right. So who knows what LHC is? The Large Hadron Collider. Okay, great. I used to work with those guys on the next big particle accelerator, which is straight, not round, but not anymore. That was a few years ago. But their old one, which still is the biggest experiment of humankind, has done some remarkable stuff, right? They found the Higgs boson. And of course, to find the Higgs boson, you have to differentiate noise from the actual event. So you have a lot of background events, and you have some Higgs events, and you have to somehow find the difference. And that's all data. It's all data-driven. They collect numbers, and then you have to look at them and decide, is this a Higgs or not? So it's machine learning, it's prediction, it's binomial classification. You can throw a random forest at it, or you can throw deep learning at it. There's a Higgs boson machine learning challenge. And it's just standard machine learning as far as we are concerned. But in the end, it's, of course, the application is physics. And they have a petabyte a day in data that they collect, so definitely big data. So specifically here, this data set is available at the UCI website. Everybody knows that. There's only 21 features that come out of the machine, let's say, and then there's 7 more that humans have made. They know the math, the formulas in physics. They say, OK, square root of this plus that. I need that because that means transverse momentum, which is important. But of course, the machine cannot measure it. You have to compute it first. So the physicists do that. They add those features to the low-level features, add 7 more. And with 28 features, the models should be better, right? You would think if you add some knowledge, domain knowledge always helps. So let's see what happens. So the AUC, who knows what the AUC is? The area under the curve of a binary classification problem. So it should be like this, but sometimes it's like this. This means it's crap. This means it's good, right? And in between, it's realistic. So 0.5 is random guessing. That's what you get with just the low-level features and the linear model. It's not quite good enough. But then when you add a better method, or you add more features, the numbers get better. So you get to about 83 if you help it. And if you get to like 76 if you don't help it, with those classical methods. Now you wonder, of course, what happens when you add deep learning to the mix. Can that do anything? And the same question was asked by some authors here in July. Actually, they wrote the answer. It was published in July in Nature, what deep learning does for particle search for physics. And those question marks were replaced by them. And you can, of course, guess. That's all you can do right now until I show you the next slides, unless you have a magical preview button in your head, or you saw the slides from last week. Who has seen the slides from last week? Okay, a few, please. Keep it quiet, thanks. So the baseline is 73 on low-level features. That's what they had. I just showed you a 76 earlier. That's what actually H2O got. But let's just look at H2O now to see what this all means, OK? Let's build a model. So this is our web interface. This is the server responding. This is our server IP address here. In our office, I'm using VPN for the last 2.5 hours I've been logged in. There's a cluster of 10 nodes. Here are the 10 nodes. They all have some information here. How many gigaflops, memory bandwidth, how many cores, 32 cores, that's 16 real cores, 2 8-core chips, Xeons, standard processors. This is, it's on-prem, but it could be an Amazon cloud. It's the same deal, yeah. It's dual 8-core Xeons, standard commodities hardware, yes?
So does this mean you can actually just run it on a single machine? You have to play like
you can run on the laptop. You can run on the laptop. Let me show you that. If I type here H2O localhost, that's my laptop. I have it running here. I can look at what data do I have. Oh, I ran some deep learning stuff. I have some weather data set that has some dates, some wind speed, temperature, temperature change, when it was like windy or not, all this stuff, right? And I can just use this, and I can say deep learning on my laptop, and I can say, okay, I want to predict the rain tomorrow, and I want to ignore the date, and this MM stuff, oops, sorry, that's too fast. MM is a feature that the authors say, ignore please, something else. Maybe it's correlated with the response. The date shouldn't matter for whether the weather is going to be bad or good, so I ignore it because it's not going to be useful, it shouldn't be useful. Now I can just say okay, and it'll probably do something, right? You don't want to look at all these options. Okay, it's running. And now it will refresh. Oh, it got it down to 7% classification error. And here you see an AOC curve on my laptop right now. So I've got a 95 AOC predicting the weather for tomorrow. Of course, this data set is not big. And now my model has 47,000 parameters in neural network connectivity. If you don't know what that means, that's fine. I'll explain that next. I just wanted to show you that it works right out of the box, right, on my laptop. This was overfitted. This model is bigger than the data set, so it could memorize it, and it got it quite right. And this is not validation data or anything. This is training data accuracy. So you have to be careful when you're doing machine learning. You need to know what it means. So I suggest you read a book on machine learning if you haven't done so. And I should also take time to do that myself from time to time, to go back and read the latest literature, which is what I did for deep learning, by the way. I didn't know anything about deep learning in the last December when I joined. I only heard the concepts. I had to figure out everything myself. All of this has been implemented from scratch again. There was an older implementation by a colleague of mine, but this is all from scratch, all again from, like, Sri likes to rewrite, I like to rewrite. Usually you learn a lot from your old stuff, then you throw it away and write it again. It's going to be a lot better. All right, so let's do something with this real cluster here. So I could just say, give me a network test, for example, and it will measure the network speed. It just showed me that from this node here, where I launched it from 85, of course it's fast, 30 gigs a second, because there's no network needed. But to all the others, it's only 160 megs a second. So it's not that great, but that's what you get on a 10 gigabit network with a crappy switch or something. That's just realistic network. So now let's see what we want to do here. Let's look at the data set. So I have the Higgs data set here, and I split it up into 3 parts. So the original Higgs data set has 10 million or 11 million rows, 29 columns. They're all just numbers. And I split it into 3 ways. Splitting it is actually super easy. I can just say split. This is a link to that link above there. It's also available under here, I think, or maybe on the data split frame. Then you can type in the key, Higgs, and you can say how you want to split it. This will split 75-25, or you can add another number, like that. This would be 25, like 75, 10%, and then the remaining 15 would be the third piece, right? You need 2 for 3. You only specify those that you need to cut it up. So anyway, let's say I did that. Now I want to run deep learning. This is my link to go to deep learning. So I just went up here, deep learning, and I pre-filled that I wanted part 0, which is 10 million out of 11. So I took 10 million for training, and the remaining 1 million I cut into 2. One is for validation, and one is for testing. The validation is used for tuning, and then at the very end I can test on my other 500,000. But of course that's enough points, so the difference is not going to be that big. But of course you don't want to tune on your training data, you tune on your holdout data that you don't train on. In this case, my source is 0, my validation is 1, and in the end I can score on 2, part 2, okay? I'm ignoring those last 7 because these are the human-made features. We don't want to use that knowledge because deep learning is supposed to come up with features itself, which I will explain to you in a second. And here all the other options are default, except for maybe here the hidden layers. I'll do a grid search over 4 layers of 100 and 6 layers of 200. You'll get to know what that means later as well. It's just a grid search, which means if I say go, it'll run actually 2 models. One with those and one with those parameters, right? And in the end, it'll score and tell me for each model what's the accuracy. So it's got it down to 40% error, which is not that great for 2 classes, but it just started, right? Oh, it's going down as we look at it. This is happening right now. And if you look at the CPU usage, you see how it's all green, which means they're all busy. All the 10 machines are busy. Now they're communicating. Now they're busy again. One node is already busy because I'm running something else in the background. I think, I forgot, I think number 1 maybe there in the middle top. Anyway, this uses all the cores, right? The machine is busy because all the fine-grained MapReduce is working. All right, so now we're back to 33 and so on. You can look at the model. You get real-time live updates. You see the whole network topology, and here's an ROC curve that's being developed. And you see the accuracy is already 76 on the validation data set, which is roughly the same as the test data set in the end, because 500,000 points of the same distribution is going to be roughly the same. So we got 76. You remember the paper said 75 was their best, right? 73, sorry. So we already beat the paper just watching it live right here on what they could do with boosted decision trees or neural nets. Right? That was the previous baseline of the physicists at LHC. So you can guess how far we can push it with deep learning and make up a number in your head. Who thinks it's more than 76? Oh. Hello. Okay, good. 78, 80, 81, 82, 83. Okay, 83. So, well, you see here, complete features should go to 81, right? So if deep learning makes up features, which some know that it can do that, then it should go to 81 or 82.
Can you explain the difference between low level, high level, and complete?
Yes, low level is measured stuff from the detector, and high level is derived, mathematically derived formulas that make up new features from the old features in a nonlinear way, like square root of stuff or cosine or whatever, some transformations. And you can click on that link on that paper there and it'll bring you to the paper. That was my previous last weekend, not this last weekend. So deep learning makes features, okay? And how does it do it? It does it by multiple layers of nonlinear transformations. So you start with something, and then you transform it non-linearly. And those next layers are also doing the same thing again, nonlinear, nonlinear, nonlinear. Every time you do a nonlinear transformation. And you need multiple of those. You can't just do one nonlinear thing and say that's it. You have to do many. And you have to reuse those nonlinear features that you just made from the previous step. You have to reuse them again. Yes?
How do you talk about the configuration of the neural net they have used in the paper? What is the config of that network?
They're using 300, and then from 1 layer to 6 layers.
What is the solver type for that?
They used Theano, which is batch gradient descent.
And what was yours, solver type? And I know the
That's going to come up, yeah. So Jan LeCun says he went to Facebook. He wrote something like about neural nets, right? Last 30 years, he's been monumental in that field. He's now at Facebook, and he says we get 89.2%, sorry, 98.25% recognition rate by a computer. Looking at a picture like this, they can look at it, distort it, rotate it virtually, and then once it's flattened in the line, they can detect features from it and then in the end say what it is. 98.2% of the time they get it right, just like humans, same accuracy. So if the human can't tell, the computer can't tell. There's no difference. So what's not deep is a linear model. It's not nonlinear. Neural net with one hidden layer. A classical neural net is not deep. SVMs and kernel methods are not deep because you put in a kernel and then you add them up linearly. You don't change your features multiple times in a nonlinear way. Same for classification trees. You're always saying, is age less than this or more than that? But that's not a new feature you then use to make another new feature. You're just saying, okay, I cut up my original feature space. That's it. I don't make new features. There is no age squared minus income. It's just income bigger or not.
More than 2 layers or something?
Yes, 2 or more, yeah.
2 or more.
So deep is trending. Everybody talks about deep learning. That's why we're here. And definitely Nature, all the other publications write about it. So Jeff Hinton and Jeff Dean, Andrew Ng, all big guys, they're all at Google now. FBI put in $1 billion. Baidu got Andrew Ng as well. I think Andrew left Google to go to Baidu recently. Apple Siri, who has a Siri phone, does use machine learning for voice recognition. So all of that is deep learning. Self-driving cars, you name it. So there's a lot of things you can do with deep learning. You saw Lequin, the guy I mentioned earlier, in Facebook now. He wrote the first convolutional nets. And he got the accuracy up for detecting handwritten digits. That was here, MNIST. I'll show that example in a few minutes. Of course, there's a lot of stuff you can recognize. People, video, whatever it is, speech, anything you can recognize, these things can recognize. It's basically like your brain, just automated, right? You don't have to grow a human every time. You just have another computer. Mm-hmm. And that's going to be very, very crazy. The future will be crazy, right? You'll have a lot of people that have no jobs because this does the job better, right? It makes the coffee the way you wanted it, or drives you to work without having a driver. There won't be need for the Uber anymore, right? Taxi drivers. Plant manufacturing already has seen lots of losses of jobs, so there hopefully will be better jobs. You can now all be data scientists and look at what else you could do with computers. But it's going to be interesting to see what can be done that benefits the world, right? Like cancer detection, healthcare, and so on. Biology is a very big field where you can make contributions that actually change everybody's quality of life. So when we say deep learning, we mean regular neural nets, but many layers. We use backpropagation, stochastic gradient descent. I'll explain it in the next slide. It's distributed. It's multi-threaded. Like all the machines are green, right? And we have all these smart algorithms. All the papers I read in the last year, all about machine learning tricks for deep learning. It's all in there. So H2O has all that. So this is a neural net. You have numbers coming in, age, income, employment. And you propagate those numbers through. You do some multiplication, additions, and so on. And in the end, you get 2 numbers out, either married or not married. Or as we call it, single. Who's married here? Okay, great. So you should have a 1 there, and I should also have a 1 there. And everybody else has a 0 there, if it gets it right, right? So now how do you make that prediction? You put in a number, let's say 0.3, then you multiply that times the weight. The connection is the weight. So there's a weight, whatever you want to call it, between I and J. And that number is just a float. It doesn't have to be more precise than 7 significant digits or something. And then you have a number for all of these connections. And you add a bias term because you want this number to always be 0.3 plus whatever these neurons say. And this 0.3 is this bias constant offset. So you add that offset in, you get a number summed up. All the incoming neurons plus the bias give a value here. And then you compute a nonlinear transformation, in this case 10H, hyperbolic tangent, or something else that's kind of smooth and differentiable, but it should be like somewhat correlated to that signal, right? The more to the right, the higher or so, but this guy saturates. If you go all the way to the right, it won't go higher than 1. This guy goes up linearly, it's a rectifier, but if you're going negatively, then it just cuts it off and says 0. So with that, you can make all kinds of step functions and make your, like, you can say, is your age between 12 and 18. With a couple of these rectifier units, you can chop off anything between below 12 and anything above 18, and you can just make a signal that only exists if you're between 12 and 18 years old. And then you can stitch a couple of these together and you get like any function. Like you can approximate anything with either enough neurons or enough layers. But they found that more layers is better because it's exponentially stronger nonlinearity you can create. At the very end, you get some numbers out. Here, these 3 numbers now get taken into these 2 numbers, right? Also the same way. And now you have 2 numbers, and those are maybe 17 and 25, because that's what these weights are doing. And now you take 17 and 25, and somehow this guy has to be more than this guy, right? Because 17 and 25, you want this guy to be bigger, but it still should be a probability in the end. So you take this softmax transformation to transform 17 and 25 into 2 values between 0 and 1 that add up together to 1. And that's the math for that exponential function divided by sum of exponential function. And you have your probability, and now that's it.
So it's actually learning from an already existing set, right?
Yes, it's supervised. So now you have your real answer given to you. That's the next slide, actually, which will explain what you're doing to make this learning happen. This is now the slide that explains how these numbers that come in get multiplied through to make this prediction. That was the last one. This slide says, what if your numbers are employment, for example? It's actually not, it's another number, right? It's a string. So you take the string, full-time or part-time or something, and you make that into a number. So you horizontalize that string into possible classes or factor levels, as we call it, and then you say, are you full-time employed or not? Yes or no. Then it becomes 0 or 1, and so on for the others. And with that, now you have all numbers, and you can work in that space. Of course, you standardize your data in the beginning. You standardize response columns if it's a regression problem. All these little things get taken care of by H2O for you. You don't need to do anything. And the weights in the beginning here are random. You just fill it up with random. Yes?
Well, wasn't the algorithm that Andrew and G used at Google Unsupervised? Because it was trying to predict.
Yes, you can do both. You can learn to represent yourself.
Yeah.
And then learn the structure of the data. And we also have that. And then once you know the structure of the data, you can use it for anomaly detection or for just pre-learning. But most people usually have supervised problems here, right? They want to predict something, and they have a test train set, and they want to just, like a random forest. So what if you have a 1, you're married, but you only got a 0.8. You have an error of 0.2. And that error of 0.2, you can then either do a mean squared error and say both 1 and 0 were not achieved. Here I was off by 0.2, and here I was off by 0.2. Together they're off by something squared. Average, that's your mean squared error. Or you can say, I don't care what my single value was. Of course I know it because together they're 1. But let's say I have 15 classes. I only care about the class that was correct, right? That should have been correct. Was I a buyer of this switch and not the other models of hardware routers or whatever? Then you're saying, let's look at the one number that you should have gotten right. That should have been a 1. I wanted to predict you bought this particular switch and nothing else. If you're not that number, you get a penalty. So you take the logarithm, which just goes through 1, and you take negative logarithm, and it goes up as much as you're basically off from 1. The more you're off from 1, the higher your penalty. And that penalty function is called cross entropy. That's what we use for classification per default. This penalizes the one thing more that matters than all of them equally. Especially if you have many classes, it's very important to use this one. Okay, so now you know how wrong you are. You know your error, right? You can plot that error curve for each weight that you got wrong by computing the gradient of that error curve at that point. You know which way to go down in the error curve. But now, of course, that's a lot of work to compute the gradient of this error curve as a function of every single weight. This weight space is 100,000 numbers. every single weight was off a little bit. You need to find the gradient in 100,000 dimensions to go the right way for each weight, how to change it just the right way to get to a better point. And then you know you have to go to the right side here to go down. You don't know how much you need to go to the right side because you don't want to compute this whole curve, right? It's too difficult to do that all everywhere. You just compute it at one point where you are right now. That's your weight right now. This is your weight. You don't have this weight here. You would have to compute it first to see how it would look like there. All you have is a point evaluation of the error function in 100,000 dimensions. And now you need to go somewhere. So you need the learning rate to tell you how far to go in that direction for each weight. So the fastest way to do this is with backpropagation, where you compute the error for one point coming in, like one user input comes in, single or not, the number was wrong. That error that you got is a number, right? 0.2 here wrong. Now you need to know how much you correct all these weights and biases to fix it. And that number gets propagated through this network. The same way you propagate it forward, it goes backwards. And you can somehow magically propagate those errors back. With basically matrix vector multiplications, you can fix up everything. That was the invention in the late 70s, I believe, that made it possible to even do this. Otherwise, it would have been way too slow. For each weight, you would have to compute a pointwise delta in every one of those 100,000 dimensions and see what happens to the overall energy or error function going plus and minus that weight. So thanks to chain rule and differential math and so on, you could figure that out. And then we know that it's just some kind of good scheme that propagates the errors. Once you have that scheme, you're good, right? You can now take a point, make prediction, fix it, make prediction, fix it. And you just go and change those weights until you're converging. So now that we have many machines, what do you do? OK, so you have this KV store in Java land, in our JVM. And you also have a set of weights that you made in the beginning. And now you're changing these weights somehow, right? But you have many machines. So what you're doing is you send these weights to all the 4 machines using a logarithmic tree. So I send it to 2, they send it to 2, and so on. And then when all the machines have these weights, then we update them. And every machine says, OK, I got my model. Let me push points through, fix it, and do that over and over again until my model looks better. So all of these different machines have a new model, different model. But note that all these machines here each have one model, but they have 32 threads running on it, right, or more. So all these threads are updating the same weights. They all access one matrix of weights of the model. And they compete for reading and writing. We don't lock, but that's fine. It's called hog wild. And that leads to a speed up. Otherwise, you have to lock, and then it becomes serial again, and everybody competes. It's not efficient. So all these machines update their model, and then in the end, they average their model back together into one new model, which is kind of a regularization by itself, because you forget about the small little details here and there. So it might be actually a good idea to run on multi-nodes if you can. But you can also just add L1 penalty, L2 penalty, for those who know what that is. You can add other penalties, a dropout. I'll show that in the next slide. But either way, you have a new model, and then you put that back into the KV store automatically, of course. You can look at it from your browser, say, what is my model like, just like I did earlier. And then you start again, and this is all automatic, and of course, keeps running for as many epochs as you said. An epoch is one pass of your training data. If I give you 1,000,000 points, and I say run, then the method will say, how many points do you want me to run per such MapReduce iteration? Like here, how many points should be processed? You don't have to process all the 1,000,000. You can tell me run just 5,000 at a time. And then if there's 4 machines, then each will do 1,200 points. And then when they're done, they aggregate again and then starts again. And then the next 1,200 points per machine. But all these machines have a piece of those 1,000,000 points, or 1,000,000,000 points, right? They all have a piece because it's cut up in the beginning under the distributed system. The file gets chopped up across all machines. And for really big data, you don't have everything everywhere. But you can. There's a flag that says send the whole file everywhere. If it fits onto your 60 gigs heap on each machine, you can send the whole data everywhere. and then everybody will sample those 1,200 points from the whole data set. So it's basically like a random forest bootstrap aggregation where you have random sets of points presented to the algorithm, sample from the same full distribution.
Question.
Yes?
Why did you choose to do a binary kind of distribution of the data for the map review, for the map?
That's a logarithmic tree that's better than if you had to send it 4 times for one guy. Because then the one guy's network is the bottleneck and he has to do a serial broadcast from one guy to all the others. Let's say you have 100 machines. You have to send 100 sends and then 100 receives. So that one network interface has to send 100 times the model size. Otherwise, you send it to 2, they send it to 2, and then the network card on my machine is not doing as much. It's only doing less. This is a broadcast and reduction pattern that's used in high-performance computing. And we use the same. It's basically the fastest way to spread it out. You send it to your friends, they tell it to their friends, and so on. And after 6 steps, you're in the whole world, right? Something like that. All right, so the secret sauce now is not to just run this and hope for the best with some learning rate, but to actually use an adaptive learning rate, that every neuron knows what its learning rate is at a given time. Adaptive automatic, like you don't care about anything, you just say go. And it'll figure out how much to change the weights for each single neuron. And of course, there's regularization because you don't want to overfit on the training data. You want to keep it generic, so your weight should be shrinking over time. There's like a decay on it that says pull me down back to 0 all the time. And your weight just gets shrunk if you don't do anything. Unless your update says, no, I need to be bigger, right? And then they fight, and then at some point they establish at some level. But you kind of have to work for it. You don't just line up there in big number space for nothing. Yes?
Can you see somehow if before the weights get added, there's a huge divergence between them? Because that would mean that they're overfitting, right, basically? So before you do W equals W1 plus W equals, is there any way the user can see that the weights are actually different? Very different?
That is actually a good research topic, right? If you don't average them, then your map reduce doesn't get fast. Because right now we average between the different nodes on the way in that logarithmic tree roll up from the network. So these 2 machines aggregate, and then they send only one model. Right. And then those 2 aggregate and send only one model. If you send all of them to one guy first to say, please evaluate them all and look at them all and now figure out which one overfits, is there a bias, shift, whatever, then it's more work for the network, but it might be more accurate. So that's a question of like, what is it worth, right? Maybe you don't want to think too much, just do. Maybe you want to actually think more and do some kind of GLM fitting of how much of each model should I use to get the best validation error, right? You can do all kinds of stuff.
So by doing that,
Yeah, go ahead. I'll get back to you.
While adding the weights, right? You're still doing that in a reverse tree kind of way, right?
Yes.
Is there a way to do it in a more centralized kind of way? That sure, you could, yeah. You could put them all into a different key. Each model could just be put into a key in the KV store, and then anybody can say, what are they, right? Is that set up in your system?
That would be easy to add, right? That's a one-liner, basically. Instead of where you say, I'm done with my model, instead of saying, let it get back to the guy who called everything with one model, you can just say, no, I'm going to put it into a key. And everybody knows what those keys are. And then any one machine can then take those and do whatever they want with it, or in parallel or whatever. You can do all kinds of stuff.
It should be more accurate, right?
It could be, yes, yes. Yes?
Two questions. So what is the idea behind that Google stuff? And then the second is it matched with the requirements of Hogwire? I mean, in terms of convergence theoretically?
Yes, so the question was whether ADA delta, what is this about? There will be a next slide actually that explains it, and then whether it matches ADA grad or not, or how is that related. So ADA delta was a student that went to Google to improve ADA grad, and he wrote a paper about it. And it actually works well even for large distributed systems. So this is, yeah, it's definitely working. And he also founded his own startup for deep learning with his method, basically.
So it's matched with Hogwire, right?
Yeah, for Hogwire, there's no problem because it's just the learning rate. It's independent of Hogwire. It's just the right number to change it to make the update better.
But at what point you're doing it is still a hog-wild race condition. And then there's grid search and checkpointing and so on, right? There's all kinds of features that you need. So this is the adaptive learning rate. I'm not going to go into too much detail. It's just more for those who want to see it later. Basically, there's a moving average, a rolling average that's computed of the change of weight. And then there's also a some kind of a, you look at how much did I change in the past over a given time window, and how strong is my gradient. And based on how much you did in the past, you keep doing that kind of way. But if the gradient is very, very big, then you don't jump all the way up. You follow it slowly, because if the gradient is big, you figure that next time it's still going to be big. So you don't need to rush it, basically. It might be a one-time mistake that the gradient is high. So there's kind of a damping effect, and this is kind of a momentum effect, and together they're doing well. And this is all automatic. All you need is 2 parameters, and it doesn't matter what they are, basically. Those 2 parameters, they don't change much. So it's a very stable algorithm. And there's dropout. Dropout means the neurons are blind. It's just like you hold your hand in front of your face when you're watching for somebody to throw a ball at you. You can still see what's happening, right? You don't need to see every pixel sharp at all times. And the same thing here. Which neurons, which connections get left out changes every time you send a new point through. So every training point, it's a different network topology, which means you're averaging exponentially many models, basically, and you have a super ensemble trained in real time, so to speak. And they all affect each other a slight little bit, but it gets more robust. Yes?
Sorry, I didn't get the idea behind the previous slide. So you say when the gradient is big, the alpha norm, which means we are not still to the point that the gradient vanishes, which means we are far from the good point.
Yes.
Then what is the idea here? To say don't update much? Or?
Yes, don't update too much. This is the RMS, the root mean squared over a moving window. Over the last, let's say, 100 updates, what was my average gradient in that window, right? You're asking, how much did I change in the last 100 updates? And if that was a lot, then that means that it's been going on for a while, then that gets you down a little, that reduces your rate. Because you don't want to, it's both ways, right? Once it prevents freezing, because if the gradient gets small, you go up, right? The rate gets bigger. So once you start becoming like the gradient doesn't change much, or it's small, then you still want to encourage a little bit of change. So you can think it that way. If the gradient goes to 0, then your rate goes up. But if your gradient is jumping around wildly, then you say, whoa, 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 take it easy, right? It's basically a damping factor and a chance to get it right. Because this is an expiration date, right? This time window here, it's only for right now. There's a moving window over the last 100 steps or 1,000 steps or something. And if you change that window length to something that's really short, then it becomes more like Aragrad, where it jumps around. Or sorry, Aragrad was the other way. Aragrad said, look into all past, all history. And you would basically not have a moving window. That was the big achievement of this method, to have a moving window that says, I don't care what you did 2 days ago when I started training. All I care about is the last 1,000 updates. So this way you are more robust to new developments. Otherwise you forget them and you freeze into the wrong space.
So how is it in terms of implementation? You need to keep a history of updates.
You double the model size.
So the thread or the process does not die when you don't with one step. I mean, you do a lot of maps, then reduce, and some maps. Are the maps, do they go away?
Your model is twice as big. You not just only store the weights, but you also store these deltas and stuff. Like you have 2 things to store. So your model doubles in size. So for MNIST, who knows MNIST? It's a digits database, right? You have single digits. Each one is a picture, like a picture of 28 by 28 pixels, and you're trying to figure out what it is. And deep learning can do well for that. Even the world's best method without using distortion. So you can change this and make the 6 left and right and all that, and make it bigger, rotate, and you become better because you make a data set bigger and generalize yourself. But we don't do that. We just take 60,000 points, 10,000 tests. It's a very small data set. It's way too small for nowadays, but it's like 30 years old. Right? Back then it was big. The best method can do 0.83% error on those 10,000, which means 83 are wrong. And all the other 9,000 so and so are correct. That's the best method there is that just takes this as a vector of numbers and says predict, like random forest. Random forest would be giving like 2 or 3% or something. But deep learning does 1% or slightly below. And ours does 0.87. At least that's what I figured out, what I could do it with 4 hours on 4 nodes. Now that we have 10 nodes, I should try again and get this down to 83 or less so we can say we're better. But as you all know, 10,000 points, statistical noise is going to be plus minus 3, 4, 5 points, right? Easily, if not 10 points. So why should I bother about 4 points being off? It's just noise. But basically, you get wrong the 4s, the 7s and the 2s. Those are slightly off because they look like the same. And if you just look at those images, you could probably manually make a filter that says, okay, if that pixel is set, then change it a little. And then, of course, you're cheating, right? So you don't want to do that. This is just standard off-the-shelf algorithm. Press go, and it comes out with 0.8%. And this is world-class. That's not easy to get done. For this, you need dropout, you need adaptive learning rate, or you need to hand-tune the learning rates perfectly with decay, momentum, and all that, which we also have, right? We have momentum decay, annealing of the learning rate, all kinds of features that you need to do this by hand. But now you can just say automatic go, and it works, and it gives the same numbers. So this is a weather data set that I showed you earlier. That's nothing special. The grid search is pretty cool. You saw that earlier. You always want to do that and run a few epochs on a grid search to get an idea of what works, what doesn't. Sometimes the rectifier is better than the 10H. Sometimes the other way around. Depends on what kind of function you need to approximate. More hidden layers means it's more nonlinear functions, right? Bigger layers means more resolution. You can see more features. Depends on what you need. So in this eBay case, Nahum is here somewhere, I'm sure. Oh, he must have walked out. He was involved with this. There's basically a user types in something when they're trying to sell something, and you need to figure out what that is from the text, right? So you can say, okay, somehow you do word to vec or something, you make this word vector, the word string thing into a vector of numbers, which word is in there, or what kind of word n-grams are in there. And from those, you have to then predict what it is. And there's 467 classes for this data set of jewelry and watches, I believe. Yeah, jewelry and watches here. In this data set, there's 467 things. And I need to tell you, is this a man's steel Daytona, or is it a women's, whatever, Cartier ring or something? And those classes are all, of course, not easy to predict. If you have random forest or 8,000 columns and 400 classes, it's going to be tough, right? So on this one, H2O needs 3 hours on 4 machines to get to a 11% error on those hundreds of classes. So the test set only had 143 classes, because it's a smaller set, but it's still not easy to figure out which class it is, right? And it gets it right 88% of the time, hit ratio 1. Hit ratio for the top 5, 96% right. So it's pretty good, and that's just off the shelf. I didn't really tune much. I just ran it with 3,000 layers here of rectifier with dropout. Everything else is default. 10 epochs is default. Yeah, it's all default. I just added a little L1 penalty to get some weights down because there's so many of them. I'm not sure that helped that much. You would probably could do a lot more.
Sorry.
Yes?
Sorry, more questions. But the L1,
sure.
How does the L1 work? Because you are taking average, so you will take away everything.
Correct. Yeah. If you have a L1 means basically penalize that guy to go down to 0, but then someone else might have a non-zero. Sure. But that also means that they needed to have a reason to make it non-zero, right? So whatever they were training on would have had to be, no, I really want this to be non-zero, even though my potential is pulling me down with a strong force, I still have to be non-zero. So, I mean, model averaging doesn't always hurt, right?
So the data should be uniformly distributed, right?
Yes, yes. You don't want to have a bias in every node, right? That would be the worst case. If you give me a data set that's sorted or has like every 50,000 points, there's a totally different thing. Then I would shuffle it first, which means it's a global shuffle, which is expensive, right, in a distributed system. So basically, it scales in parallel. We ran it on 64 machines, of which one was dead, so 63. And it's only 30 times faster, you say, on 60 machines. Well, one machine is zero communication. 2 machines is some communication. And all of these have communication. So actually, we should have compared from 2 on to 60, right? That would have been a fairer comparison. Of course, you're not going to be 60 times faster than 1. There's absolutely no communication required, network communication. So this is, next time I'll probably plot it from 2 to 60 and look at whether this improvement is 30 times. But it's by definition, it's distributed. And once it's distributed, once the network is over, the sending part, then they just train. And you can say, I want to train for 5 billion points, even though there's only 50 training points. I just keep repeating on each machine. And after 6 years, they will say, OK, now send it back. And then, of course, the speed up is huge. But it's not really the speed up for accuracy, right? It's the speed up for how many cores are running, basically, how many points you can process. What you really want is time to accuracy should go down. And we've seen that also to work well. But it's a tuning question, right? You have to figure out how many nodes, how big is your data set, and so on. This is just a quick example of the unsupervised stuff. You want to figure out what an outlier is in this data set. Each one of these heartbeats is 200 pixels, data points. You can learn the structure of this data by going to 20 neurons. And those 20 numbers that are in here, that are encoded from those 200, they contain enough information to make it back up to 200. That's called an autoencoder. And if your error is small, which it is in this case, then these neurons have learned to represent the heartbeat in those network neuron weights, right? And now you can put in a test set and say, push me through the network. And what comes out is something that looks like the training data, the good heartbeat. And you don't see the hiccup anymore here, right? This is what the network thought a heartbeat should look like. And then you can compare this and this, and you see that there's a huge difference from 0 difference to like 10. So there's an outlier somewhere. And this is what you can do to do nonlinear anomaly detection through nonlinear PCA if you want. This is structural recognition intrinsic to the data set. Of course, this is not easy for big data. If you have 8,000 column eBay data set, you're not going to find outliers everywhere. I mean, it's all noise, right? Yeah, it's kind of a question, what's good data? How structured is your good data? So for the Higgs data set, I could have taken all the zeros and said, train. That's my background noise. Learn the structure of background noise. And then I could have thrown in an actual Higgs and seen whether this would have found it, right? That's a good test. Yes?
So when you use anomaly detection like this, you have at least as many nodes as you have rows in your data table, right? Because you want to basically re-output the same output.
In the end, you have the same, but in the middle, you don't have to, right? So these 200 turn into 200. That is hard coding. You can specify these 3. This could be 25, this could be 100, and this could be 93. It doesn't have to be symmetric either. You just give me the hidden layers, and I say 210, 210. And then the network learns to make this work. It just fixes the weights until it works.
Well, my question would have been, what is the hard limit to weights? So basically, all the weights have to be on one machine, right? Once they pass. Oh,
the weights have to fit on one machine, yes.
So for 8 gigs, let's see, how many weights can I put? Like you're basically.
That's a billion weights, right?
Okay.
Normal models are like millions.
Okay.
Yeah. So this is never a memory problem. The only memory problem here is the data, never the neural net. The neural net is millions of weights. That's it. You send around 50 megs, 100 megs over the network. You're never sending around gigabytes. Yes?
In that case, a data point is the entire one?
In that case, 200 pixels was one heartbeat.
Oh, okay, so
I just plotted them one after the other. These were 20 points. It was a small data set. So R, if you know R, you know how to use this, right? It's H2O.deep learning, and there's an R vignette that we wrote, 17-page or more document that explains everything about deep learning from R, H2O deep learning. It explains the activation functions, the training points of whatever momentum rate, adaptive learning rate, standardization of the data, MNIST example, grid search, checkpointing, everything. So if you want to know how to use this, you can just go to this link here. It will guide you right to that vignette. And you can get the slides. I'll post them on the Meetup site. All right, we're almost done. Hang in there. Just a little more. There's the POJO. Who knows what a POJO is?
Plain old Java.
Yes, plain old Java object. So it means it's just Java code, right? That's the thing I mentioned at the beginning, the scoring code. So if you run a deep learning model, and you click on Java model on a web API, you will see an instruction that says curl server deep learning model view Java, .java instead of .html. You can just type .java in the browser. Let's do that real quick. So here I can just type Java. Oh. And here I have my Java version of the neural net. Of course, there's a lot of numbers, but this is the code that tests your points, right? This makes predictions. But of course, this is still heap allocation. I didn't inline all these calls into register long. I mean, I could write like 10,000 calls of function with different names, and each do a kilobyte or two of multiplication that are hard-coded. Then it would be even a little faster, I think. But just to load all that code is still going to cost some cache waste. So I don't know what's worse, basically. Storing the weights in a separate object, one long float array, and then using those, it's probably not too bad. All right, let's see what we got here. So now we should be at the point where we are asking, what did the Higgs do, right? Yeah. So let's see. So we got to 76 earlier. You saw that live, that 1-minute demo. And now let's see what we got out of H2O. So if I go to that server again, there's model, there's a score, and then on the score there's multi-model scoring. Okay? And this is something that says data sets, and I can see what I have here, my Higgs, my different pieces, or I can say, show me the models. So now we have those two deep learning models that we ran from the grid search earlier, but we also have these three other ones that I built, the random forest, the GLM, and the GBM model. Gradient boosted trees, generalized linear model, and random forest. Those were part of the baseline. This GBM was a baseline. So now I'm going to say, score me these three, these five, score on the last bit. Okay, part 2, which is the last 500,000, which is my test set. None of these models was trained on that. And now we have real-time scoring almost for these 5 models on the test set. And you see here what the parameters were, and you see the AOC curves. It's a little small on this screen here, but you can tell that deep learning, it looks a little more like a curve than GLM. It looks more like a line. Now, of course, you want to do more than that. You want to do advanced. And you can say, look at the AOC curve. If you click on this one, deep learning is the winner. What's the AOC on that guy? Let's plot it. Let's look at it first. AOC 79, 76, 76, 75, 59. So the deep learning model, the faster one, that one was trained with the 100, 100, 100, let's see here, this one, the 100, 100, 100 model, 4 layers of 100, only 10 epochs. That trained fast. It wasn't a long time to train this model. This was the scoring time. Let me look up the training time. The training time was 132 seconds. That's faster than the random forest to get to the higher accuracy. This one had taken 300 seconds and it's 0.8 almost, right, instead of 0.76. And it's also faster than a random forest. And our random forest is really fast. So now,
what's the difference between the first two deep learning?
it was the yellow things,
Oh, yeah.
the number of hidden layers and the size of each. This is a fast model, only 10 epochs, right? It's not that big a deal. Let's look at the advanced tab real quick and look at another visualization here. So these are the ROC curves. This is also random forest. This is deep learning. This is deep learning. This is GLM. I can say make a new visualization of the training time versus the AUC. And I get another plot here. It shows that the highest AUC was reached by this deep learning model in half the time that it took these two. This is random forest. This is GBM. So when you say deep learning is slow, that's not always true, right? Because you can say, hey, only train on like 0.1 epoch and make a very small network. And then you're fast. You can be way faster than random forest. But of course, you get an online training, basically. The more you train, the better you get. You don't have to train forever. But often you're better than other models, quicker.
What do you mean by 0.1 epoch and 1 epoch?
You can say process 0.1 epoch, which means sample 10% of your data collectively on the 10 machines. So every machine only makes 1/100th of the data and processes 1/100th of the total data. So if there's 10 machines and you cut the data up into 10 different pieces because it's a petabyte of data, every machine only has its 1/100th, its 10th of the petabyte, right? 100 tera, let's say. Then you can say, process me a bit of that and show me what's coming out. You don't have to process everything. Your mappers will just say, take this point or not. No, take the next. Okay, take. No, don't take. And every point they take, they just multiply through the network, backpropagate the error, and update the weights. But those that don't take, they just skip. That's really fast. So you can parallelize this whole processing, and it's also sampling if you want. That's the strength of this, right? You don't have to go through all the data points just to get the model. You can get a model really fast. But of course, the more you pass, the better you get. So usually you want to go through 100s of these epochs over data again and again and again, because it is an iterative method. Iterative methods take longer. So this was this. Yeah, so this was already better. Last time I got a set 0.8 here from that model. So you see that the hot wild race conditions of these machines and their averaging, all that doesn't add up to the same exact model every time, but it's kind of close. So 0.8 was achieved last time, and that's way better than the 73 baseline, right? And that was in 260 seconds. A few minutes. All right, so now back to the paper and what's possible. So I've run a 3-layer network with 3 times 1,000 neurons. It's way bigger instead of 100 or 200. And then 4 layers with 500. And also 6 layers with 500. And I've seen the last number today was 0.873, so getting close to 88. So that's what the paper reports. They had a half year to get those results, right, using Theano and a GPU. So we're getting close. We're actually beating them on the 3 and 4 layer networks, which they have taken 300 neurons, and we have 1,000 or 500. So obviously we beat them, but it's still a remarkable achievement to get to 86, 87%. And that doesn't take that long, right? This takes a few hours to train. And this competes well with a GPU solution because it's out of the box and easy. You don't have to do anything. You just click and you say, you change a couple numbers to 1,000, and you change L1 penalty to 10 to minus 5, and you say go, and that's it. You can download this yourself. The link is there. The data set is there. So this is the Higgs particle. And now we're almost done. So this is the last overview over tips. So if you have any questions how to run something or whatever, then please read this or ask me again. So, sorry? They used CUDA, I think. It's Theano is Pi, Scikit, PyLearn. So more layers means more complex nonlinearities, right? More neurons means more structured memorization. Regularization helps against overfitting. You need that, especially if you want good validation error. So otherwise, the validation error goes down and then goes back up again. And if you add L1 and L2 penalty, the validation error goes down, keeps going down until it flatlines and noise. Rectifier is faster than 10H because the function is simple, it's 0, 0 or linear. And then also because it's 0, you don't have to backpropagate because the gradient is also 0, right? There's no change no matter where you are on that left side. So you make your network sparse and you don't have to do as much work in the backpropagation. Of course, it means that all your functions are approximated by piecewise straight things, which might not be as smooth as a 10H. But 10H is a little harder to compute, and also that the gradient is non-zero everywhere, which means all the backpropagation takes longer. Backpropagation means change of weights, change of numbers in a matrix, which costs more computational time. Dropout is important. You can specify input dropout. So if you have a lot of input, like I said earlier, you want to see only some of it sometimes because it might be noisy. But if all the input matter, then you want to see them all. You don't want to just say, I forget 30%, I don't care. No, you do care, right? Data is usually important. It's just that it's noisy data, then you don't care. So the input dropout is only when it's applicable. The hidden layer dropout, just in general, makes your features a little better because they take longer to train because they don't learn as much from zero out signals, but once they learn something, they're usually more important. Ada delta is important. That's definitely useful. Everything is distributed, so you can process more points. But of course, if you're waiting for 6 years before you communicate, all these models will be totally different. And then you average them, you lose everything. So you don't want to do that. You want to say, maybe do 2% of the time in communication. And that's actually my default. If you don't do anything, 2% of the time will be spent in communication. It's auto-tuning. So you don't need to do anything. That seems to be a reasonable value. If you want more than that, you can look at the number and change it by hand. You can hard code the number in. You can stop the model at any time, and you can continue the model at any time, and just say continue from here. And then you can change that number, how many points you process per map reduce iteration. So you can say, okay, let's just go with default. If it doesn't work, then you say, okay, let's make the communication more, fewer points per iteration, and suddenly you have more communication and a bit more alignment between the models. But of course, it gets a little slower, but maybe it gets more accurate if you really care. If you want to do a Kaggle contest, you might consider these things, right? And if you have imbalanced data sets, like all buyers but no non-buyers, then you want to set balance classes to true, which does some probability math to correct for that. It upscales, oversamples, undersamples the distribution so that you get 50-50 to the model, and then in the end you correct the weights, the probabilities back to the original prior distribution. Yeah, that's about it. There's some replication of the training data if you can, right? That makes it better because every model is built on the full data set by sampling a subset. And if you cannot store all the data everywhere, then you just leave it off and turn replicate training data off. I don't detect it automatically right now because usually people have 60 gig machines and only a gigabyte data set or something. So if you have the interest and the patience to code a little bit, then there's a lot of work left to do. Convolutional layers, pooling layers, right, for images. If you want to detect faces, you need to do more than just look at the pixels of your face. You have to look at noses and eyes and stuff. You have to detect structures. You have to look at those 30 by 30 subpixels up in the left corner and right corner and so on. And those pooling layers achieve that. Anomaly detection could use some more work. Stacked autoencoders for pre-training. You can say learn layer by layer instead of trying the whole thing at once. Even though every time I ran it, it just worked. But maybe it's faster if it is stacked autoencoders. Who knows? I've done it in the past, but it didn't seem to need it. GPU support will be useful, right? If you have a GPU or OpenCL AMD machine or something that can just run faster if you enable a flag somewhere, that will be useful. Recurrent neural nets are very important for language sequence processing, where you make submodels, so to speak. You look at the sentence and make a meaning out of it. You don't need to look at everything. Benchmarking is good. Kaggle competition, right? Let's do some more Kaggle if you need to win a Kaggle competition or have nothing to do on your weekend. Like me, I guess, even though my wife is expecting a baby, by the way, in 2 weeks, so it's gonna be home. So no more Kaggle for me. other optimization algorithms, Hessian-free, conjugate gradient, LBFGS. There's all kinds of stuff that one could potentially work on. For smaller data, it's better to do something more accurate than to do stochastic gradient descent, right? Yeah? These are filed JIRAs, which means they are open for work, and Hexadata isn't the only one working on H2O, but we are the majority of people working on H2O. So there were some people working on some of these sub-pieces, but they're not claimed by all means. So if anybody has interest in working, you can also add your own tickets, right? This is open source. So if you do something good, you fork it, you add something cool, we'll merge that, and we'll get that into the main product. Yeah, so basically that's it. So it's distributed, it's in memory. I hope all of you are convinced that this is the case. It runs on big data. And deep learning is cool, right? It wins stuff, and I'm actually pretty encouraged that the Kaggle competition is led by us, by this thing here. And the Java code is available in GitHub, but it's also just here, right? You can look at it. It's regular Java code. This is some loop, specialization, partial summing and stuff for the matrix vector multiplications and the forward propagation. We use all the tricks there are to make stuff fast. That's why it's all green, and that's why it's reasonably fast. But there's always some opportunity to make it better. So if anybody's interested, please talk to us. Thank you. Oh, cupcakes. Nice. Okay.
My name is Jay.
Oh, hi.
We are doing parsing for large text, unstructured text. We have some array of keywords. We built a dictionary. Like most people who use that
Well, that's okay. Yes. Yes.
Yes. No, so it's a completely different approach. It's usable medically.
How do you get the sentiment or emotion?
Emotion. In the doctor-patient communication, it's heavy emotion.
Oh, I see. So you look at if the word says don't like or something, or I hate
so
or
it's
something.
like eBay, you're figuring out what's happening, what they're actually saying. So here it's far more important because basically one of the predictions is you're interested in suicide. It's a trend. I can't catch you the day before you're suicide. I'll catch you 5 years
early indicators.
and then start working on you as a psychologist.
Yeah, that's interesting. No,
So is there some difference between Ox data that
yeah, I mean, I don't know that there's any expert in our in-house about that. Probably not.
This expert needs to
But
be applied to.
if you have the vertical knowledge, right?
Yeah,
then
we
you
have
should
the domain.
definitely then you should definitely talk to us.
So
To
the
Sri.
card or
You should talk to Sri.
Sri,
The
okay.
guy that had there, but I can give you my card as well, so you don't forget the. Here we go. Great. Thank you.
Hi, I'm Ashish. We connected over email. Remember that about the extracting the features of?
Oh
the,
yes.
Yes, you.
Does
so
that
you
work for
pushed
you?
out. Yeah. So I got actually. So how? I mean, I actually got stuck in like, running that JSON package because that JSON was not working on R. So like, I mean, I could not even connect. So because because you're saying like it's built on like 3.1 something like. There was some kind of version issue. I was using R Revolution Analytics.
Yeah.
And I was not able to connect it. So, but I want to fix that. And somebody else in the organization basically does that, right?
It has to be 3.1, right? I think it has to be modern somehow. I don't know what the reason is for that.
Yeah, JSON was saying like an older some version. But anyway, how have you incorporated that? There's a new parameter in
yes,
the
I can show you right here.
Oh.
So if you look at the screen there, I'm saying I just ran the model earlier, right? I ran this deep learning model on the weather data. Remember?
Yeah.
This was the weather data.
Yeah.
And now I can say model, deep feature extractor, on the model here. This is a normal.
But now when I load, like I had a data set which was like 1.5 gigs. It doesn't load on this side. It just fails. I mean, if I have a data set which is like less than.
No, a gig is nothing, right? It should be no problem.
It should load?
Yeah, it should be 10 seconds.
It should load in 10 seconds, huh? It has like around 3,000 features.
How many nodes did you fire off?
First of all, I forget about nodes. I was not even able to load my data.
How much the heap space do you have? Heap size, maybe. If you do java-jar, you have to also say -x and x. 10 gig, 100 gig or something.
Is it 1 or 4? 8?
I have no clue what question I
What kind of internet connection?
How do you run the platform?
One way is like
Java, right?
Upload the data here, right? There's a command called upload data, right?
Yeah, I know, but when you run the platform,
not the soil property, the Higgs one.
Run that jar file.
I tried, and I was late by one day. I had my script already, and then I tried on Tuesday to submit, and they said no, it's Monday night was the deadline.
has to be
So one thing about the completion is that like a lot of data will have like missing values, and you have to like
we handle that as well.
How do you handle this? Like
in H2O in general or in deep learning?
Like like means
so
it's not
an
a deep
imputation automatically in deep learning. For categoricals, I make my own categorical. Like if you have cat, dog, mouse and missing, then it's 4 different.
There's a H2O download thing, right?
But for the numerical ones, it's mean imputation.
Copy paste that
so it's stable against missing, but you could have better schemes, right? You could say in R you can first impute. You can do you can use an exec statement that we call it, is to say if the number is missing, then replace it with this function that's evaluated over the whole column and take like this distribution. I mean, you can do all kinds of stuff.
And you have all these like, so like let's say I want to do some kind of like I want to look at the distribution and then like based on that predict like one particular column. Is that like automatically, can you do that in
using R? Like
you have to do that first in R and then.
But it's not, you're doing the data in H2O, right?
Yeah.
You're doing an R expression. So we have a lot of tests. Here we have a lot of tests. Like if you go to R, tests.
So this is what
this one. This
munching.
Is 1 gig. You have to specify more.
So I specify like 10 gigs over there?
Yeah.
There's like these
4, 6, whatever.
expressions, right? Where you just do some stuff.
The recommended size
and
is
there's all these like if else, exec, something.
Yeah, 1.5
I mean, it's more complicated than I know, right? I don't even know what they all do.
Data munging still has to be done in. I don't use R that much. I use Python more.
Oh, I see.
So the data munging has to be done in.
You have to program it somehow.
So I'm curious. It looks like you have deeper integration with R.
R more than Python.
Is the Python integration as
I'm sure there is something called R
we have
Python.
a
There is everything Python R.
Let me
It's just
show you
easier to
Python.
program.
Yeah.
So did
no, I just need the right path.
It was saying that there's a package called JSON. The visualization you showed the CPU, and it was saying
Yes.
is it on Java or something?
This is called perf bar.
I didn't get the error actually.
It's a Linux only thing.
I think 3.
Mine is also 3.
They're doing some QA right now. Like there's always continuous integration that they're running something. So this is the Python, by the way. Here we have like whole tools and stuff that run all this, right? You can run import numbers and.
So I guess could you do everything or most of the things you can do through R?
Yeah, because Python does nothing but, in our case, it makes JSON requests, right?
Oh, okay.
So we have the whole wrappers that our QA guy uses to drive Hadoop clusters with H2O and 10 nodes, right?
Okay, so there's probably like a Python library, right?
Yes, but it's not a clean library. It's more like you need to kind of use what we do and copy paste it together. If you're a good Python expert or something, you can easily do it. I don't know, it's not bundled up the same way as our R, which just comes in the jar. Right? Everything is nice.
So everything is done through JSON. Python, yes. Python, Scala, R, everything.
Scala will be JVM native, right? Because it's a JVM-based language. Java and Scala are connected. So those don't have to do JSON.
Only with R and Python there is a JSON.
R and and you can use, like, I can look at the cluster from my phone, right? All I need to do is like you turn on VPN to my office. Then I go to the web page And here, now I have the cluster up, and I can go to whatever, admin, jobs, and I can check my last job, right, whether it's converging or not on my phone, right, because it's just a web browser. It's really just a web browser, and I'm looking at it here, right, and that's pretty cool.
So I'm curious, as far as like integration, like with like production systems, like, do you guys expose like a REST API or?
Yes, we do have a REST API that's somewhat documented, right? That's our weakness in a way, that you don't have a clean documentation of this is exactly what it does and nothing else.
Because I mean, because like if there's a REST API, you can just plug it into your system.
Yes,
and
yes.
Just,
So for example, you have this here. Let's go here. Let's look at one of these models here. Instead of typing HTML here, I can just write JSON, and you'll get the JSON back, right? And then you can just look at this guy, put this into your JSON viewer, I don't know, here, and just, I mean, obviously you can look at it differently, but this will then look nice, right?
Yeah. So do you also export to PMML?
We used to have that, but not anymore, I think.
Cool.
So here you have all this stuff, right? And you can ask what's your, like, what are my parameters? Like, everything is in here.
I definitely like to, like, at least give this a
So we have people that use it just through JSON with curl. They do nothing else. They just say, okay, submit like this command, and then they wait, and then they ask progress, and then it says, okay, redirect URL, go there, and then they go there, and then they see what's happening, and it's always like, so it's
yeah, so there's a RVGNet that you showed.
Yes.
So that's basically shows if I want to try and get started.
Yes, yes.
That's pretty decent code.
This is a good starting point. That's through R.
Yeah, I definitely want to give it.
And the web API is even easier. Right? The web API is java-jar, h2o.jar. Like you specify which jar to load, and you say h2o.jar. So you literally go in the terminal, you download the jar. You do java-jar, h2o.jar, and this guy will now launch a web server on a specific port, right? And oh, because I'm in J, I need to disconnect from this guy. Here, it didn't know what network I was in. So now it's here. It says listening to here, point your browser to this and that. So you can just go here. This is the IP address of my system right now because I'm in this network. And now I have my browser up and I can upload data, import, whatever. And then you can run all these methods. And of course, this is now a one-node machine, right? But if you have two machines, you just do this. You do the same thing, java-jar, another h2o.jar, same thing. And now you have two nodes, cloud size 2. So you go to the same API, same address, and now it's two machines.
Nice.
And if you have like 10 machines, you can run it by hand if you want, right? That's a naive way, of course. In reality, you do a Hadoop jar, and then you launch it through the mappers that then run a dummy Java jar as a mapper job, and they just wait until you kill it. But
all of them are running on the same system, right?
Right now, they're both running on the same machine, yeah.
If
but
they
you
run
can,
on different
they do
systems,
multicast, they discover each other.
They're going to do
the same network, yeah. Unless you specify a flat file with the IP addresses and the ports, then it uses those. It doesn't do multicast. So we have all this deployment version. Like we have many customers in production. Like obviously, it's.
So in this scenario, if I had two computers, I'd run two jar files.
Yes.
And each of them can have different IP addresses, right?
Correct. Totally different. Yeah.
So they would come up with two number of cloud size 2 or cloud size 1?
Cloud size 2. Okay. If you give the same name of the cluster or give no name.
Oh,
normally you do dash name also, and you say Arno and Arno and Jack, John. They all have different names, right?
So I can talk to the cluster through any of the IP addresses.
Correct, and you can submit jobs and check from
any
anyone.
of them. That's cool.
Yeah, so it's they all have a distributed KV store. But if you launch the job on one node, then it has the model in there, and then it sends it to the others, trains, and comes back. Yeah. When you then now go to the other one and say, what is the model? Then it has to send it over first to make a cached version. And as soon as you update this guy again, it says invalidate all my open copies, caches. So this guy gets invalidated. The next time you reload, you have to fetch it again. Right? It's kind of it's aware of what's happening.
So this is downloadable from your...
Yeah. It's h2o.ai, right? It's free. It's free and it's fully featured, right? There's no.
Pretty exciting.
Our goal is to get as many people interested and happy, and we don't want new money ever, right? We only want money of those who can afford it, basically. Sure. If that's then the bigger companies that depend on it. But instead of paying 10 million to a SaaS, they pay much less to us, right?
So just under the hood, like deep learning is still progressive validation, right?
The validation, if you specify a validation data set, it does it. So,
no, that's like I mean like progressive learning. Like
it's online training. Correct.
Yes.
Yeah,
because I saw the error rates.
It gets better. Yes, correct. Yes. Cool. Every point, it's online stochastic gradient descent. Every point it trains, no batch. It gets.
So when you say learning, I mean, is it you consider it as a supervisor or unsupervised learning?
It's supervised.
So
unless you do anomaly detection where you give training data, there's no labels there, but it's still kind of supervised because you give the real data, the good data, and then you give the bad data and you see what's wrong with it.
So, just last question. You can share your slides with us, right?
Yes.
Okay, cool, awesome.
Actually, if the easiest for you to do is go to Twitter. Arno Kandel is my name.
Oh, and just look at your...
And then you go down a little bit.
It's already there. Huh?
Oh, okay.
And we had the last slide here.
Okay, nice, very
Meetup screencast, and the video and the slides is from last week. It's almost the same, except for the Kaggle.
Okay, cool.
But I'll upload the new slides.
Sounds good.
Okay, cool.
Awesome. Appreciate it. Thank you.
So I was wondering, you use numerical libraries, right? Somehow underneath.
It's all our own.
Oh,
we don't call BLAS or anything. Yeah.
You don't
from scratch.
Okay, and so you wrote numerical libraries in what language?
Java.
Oh.
Pretty much everything is written in Java.
No big letters, right? No capital D for double. It's all lower. It's all.
So you wrote numerical libraries in Java. So I'm trying to compare or to contrast what Spark does with what you do. And Spark says that they in ML libraries in Spark they use Fortran and then access them through Java native interface.
Sure. Yeah, we can do that too, right? We have one instance where we once did that or something, but yeah, you can do that if you want.
I can.
Yeah, sure.
How do I do this customization? I mean.
Well, you need to know Java basically.
No,
right?
I do.
And then you just call with a Genie call. You say here's my pointer to my reference to the array of integers or array of doubles.
Okay.
And I'm now calling BLAS to do eigenvalue decomposition.
Yeah, but somehow I have to embed this code in the model when this call is due, right?
Yes, correct. So the packaging is an issue, right? You have to somehow know how to do that. So you need.
Yeah, so that's what I'm sorry. I will ask
no.
basic questions because I didn't read your website. So I'm trying to understand. You actually code only in R.
Deep learning is not that hard, right?
No, I went through. Andrew M course,
yes.
So at that level I know. Also, I had a question, just by the way. He uses sigmoid functions as activation functions for the deep learning nodes, and you use hyper,
it's the same thing. It's scaled this way and this way. It's just shifted and scaled.
Yeah. So did you do it consciously because you didn't want to use sigmoid and your approach is better?
No, he uses sigmoid because it's old school. That's what people understand. From 0 to 1,
okay.
And they like it because it looks nice.
Right.
But 10H is actually better because it's symmetric around 0. It's the same function.
Right.
To 1.
It crosses not at 1, but at 0.
Multiplied times 2 and shifted a little bit, scaled, like stretched or pushed together.
What exactly is the benefit? I just didn't get it.
So it's 2 times sigmoid plus 1 or some, 2 times sigmoid plus 2 or something like minus 1. 2 times sigmoid minus 2 or something is 10H. It's the same.
Why is it better? You use combination of this cutoff plus this.
It's easier to grow from noise because it goes both ways, symmetrical around 0. It's somehow like
if no bias.
There's no. Otherwise, you assume the 0.5 is different than minus 0.5?
Actually, I ran deep learning with his, with sigmoid, and I did get actually complete symmetrical. So he does checkpointing, and I did get symmetrical answers for minus and plus.
Yeah, once it converges, it's all fine, right? It just has to add a bias term that has to become minus 1 to make up for
there
that.
is bias term, right.
And you need to learn a bias of minus 1 stepwise, and ours just starts like that. So it's I mean, people are, it's the same thing, right? It's just an offset, it's just a scalar number and the bias.
Do you have some references to papers that explain exactly how to use these two functions in combination instead of sigmoid?
You mean
somehow, maybe just complete example would be really helpful. If you have,
Let me see. I mean, let's see here.
Oh, so basically 10h the hyperbolic tangent. Okay.
So 10h is the same as 2 times exponential.
2 times g of 2x.
Of 2x, yeah. Minus 2. Or something plus 2. Yeah. Oh, out here minus 1. Okay, then the 2 comes out, right? But I don't know. Anyway, I mean, it's the same thing, but I don't know what the benefits are. I didn't study it. I read Jeff Hinton said it's better to use 10H because it's symmetric. But I don't know why you have a hard time learning the bias. I mean, it takes a little effort to change the bias until it's at the right point, right? Otherwise, it just starts like that. It's all good.
I don't know really in depth.
At
So
the
small
at the end layer, you have to do it because you want to learn probability. So that's the why this is
correct. Yes.
In the layer.
Suppose the data set 1,000 rows. Will you give me 1,000 rows?
The last layer.
You have better data.
Well,
how many rows are there in this?
Actually, 2 inner layers.
Let me look at that.
25
and also, like, see, suppose you have
just
3,000 features. I just intuition, like, should you have 5 layers of 1,000
either
nodes?
you have to
Where should we start? How should we start?
Like,
3 layers of 1,000.
3 layers of 1,000. And shouldn't you pick the third layer as the best feature? Because the first layer will be just like a first layer transform, right?
The last one can be a little bigger.
You can make it 1,000, 1,200, 1,300. Is that what you said?
Yeah, that would make sense.
But like, I mean, if you're trying to reduce the dimensions, right? So
not
you should make 1,000.
Because you need the probability.
You don't have
something
to.
Scores
but how do you know? You have to just experiment, right?
It's cheaper, of course, if you go from 3,000 to 500. And then 700 and then 1,000 or something. But then you're basically saying, I only care about 500. Right?
Yeah, but how do you really know? Okay, first of all, like if you have 1,000 rows, the features will also have 1,000 rows, right? Those nodes, those layers will also have 1,000 rows. Right? Can you show me?
Yes. So this is this guy, right? It starts with 30.
The number of model parameters. How many rows are there in this data set? Let's see the
rows.
Yeah, how many rows?
Rows doesn't matter.
355 rows are there, right? Yes. So the feature should also have 355 rows, right?
No, rows is how many points, right?
Yeah, I mean, so the data set has 355 rows.
Yes.
So when I extract the features, it should have.
Yeah, sure. The transform data set.
The transform data has 55 rows.
Rows, correct.
Right, it should
but
be.
It has 200 columns instead of 30. It gets bigger or smaller, whatever you do. Right?
Oh, okay. So what's the original dimension here? 30.
25 or something. Some of them are categorical, right?
24 columns. Oh, okay.
Some of them are categorical.
Okay. So it explodes on the dimension based on the units. Okay.
So now if
the number removes.
So now we get this key, this model, and extract the features from this model on the metadata, and you want to get the layer number 2.
Oh, okay.
Or I think one is 0 based on the Java code.
You can't put 2 over the Y, huh? You can put 2 over there because
0 and 1.
Okay. 0 index. Okay. 0 index.
So now you have 200 columns plus the prediction. These are the deep feature creation 200. So this is your features that are made up
Yeah.
This is just a tool, but I don't know what you're doing with that, right?
But thing is that it could be, because these are transform features. It could be
interesting to look at, to do eigenvalue analysis or something. I don't think you cannot learn better with a random forest now, because you could just run deep learning.
What did you say just now?
Random forest on these wouldn't help.
On
because
these
deep learning, deep learning is just as good to use those.
I had one question actually. So for anomaly detection, you said that you just trained with one class and the other class became the anomaly, right? Is that always the case? We have to
whatever you train, your model learns the structure.
Right.
And then you give me something, and either it fits or it doesn't. And you get a reconstruction error per point, saying this is my mean squared error over those inner input and output layers, whatever they are, horizontalized, categoricals, whatever.
Sure.
There's some RMS error between those two.
Sure. But let's say I'm looking for some imbalanced data. So the one class is let's say in the case of the impressions and click data. Clicks are always, very, very small fraction of that. But I'm looking some anomalies on the clicks data that is kind of fraudulent, for example.
Then you have to give me all the good clicks only.
Okay. And then you train with only good clicks.
And then you give me all clicks coming in.
Okay.
And I tell you good. Oh no, something weird, good.
But I don't know which one is good, which one is not good.
Well, those that fit the original ones that you trained, right? That have the same structure.
Did you do the same thing with Higgs boson?
No, I haven't.
You haven't tried that?
Okay,
but it's a good idea.
You know what I mean?
Yeah.
You basically learn only on the good data, which is only the click stream, those that clicked and they're not fraud. Somehow you need to know, right?
Okay.
And then you train on that, but then until your reconstruction error is really small, like you have to seek some convergence. So when you start training the autoencoder, check autoencoder, it will start with the error if you have all noise data at the beginning. That's like your burst reconstruction error. And then it should get lower. And at some point that's what you get, the best you can do with whatever model.
In a large data set, let's say in the gigabyte, billions of the rows, and you have the distributed neural network, then in that case, if the sum of the data is, sending to the specific nodes, the other patch would become like an anomaly, right?
Somewhat, yes. There's a little different bias.
Yeah, a little different
yes,
bias. So do you think any kind of, solution?
That's why the model that's trained, the outlier anomaly model that learns the good data is an aggregate, right? It averages. So it kind of is good for everything.
Yeah. Okay.
So
how do you distinguish characteristics of bad clicks? What are those? Can you actually reconstruct the features? If you can, then maybe you do just something else like anomaly detection without.
Yeah, that's the problem. We don't know which one is good, which one is not good.
That is good only if you have very unbalanced data, like 90-10.
You want to discover what is bad about it.
There's no way to cluster.
60-40. Only you have 10-90, then it's a good idea to go through
many dimensions. And
I guess.
You don't know which one is good, which one is not good.
Yeah, I mean, otherwise you're wasting the data. I mean, you're not using the bad data.
You're not throwing it away. You're just looking at the events that matter to you, which is very small.
Yeah, that's the challenge.
So if you find at least one dimension in which it is the case, then you can just do,
you're not making good use of the information
of this dimension and see whether it's outlier in the distribution.
Yeah, maybe in the one dimension is outlier, but in two dimensions, when you look at in the two dimensions, it's not outlier.
I can just download this whole matrix.
Right. So you have to construct features in which it will capture
export to a file to. I cannot do export to CSV.
You can do this.
Yeah, that's a challenge.
You can do CSV.
You don't know it.
You don't know. Users are no desktop.
So that's
maybe the rate because it's a bot or something like
text
that.
or CSV.
Well,
And now
if
it
we
was
just
written.
know that, it just detects that
So
all
if my file is of 1 gig,
specific
he just advised me that I should
we
put
need to
4,
figure out
should
what
put the number 4
patterns
over.
are abnormal.
So for that, you actually find out what hardware.
Because I probably like, I would not get stuck in this JSON thing. I can directly go through your API and I can be very fast, right?
Yeah, that's
I
a
mean,
problem.
the
You don't know
writer's
which
not
one
that
is
fast.
bad.
It's like 100 megaseconds.
It doesn't help.
No, I think that the distribution.
Yeah, but like there's
if
a
you
lot
can
of hit and
construct
trial you have to do
maybe
on
you
that
know
because you
Gaussian
never know, like,
distribution
1,000
as a function of whatever you
you have
you
to
observe.
start somewhere.
Say, you
Do
know,
something small
outlier
first,
in
200 by
Gaussian
200,
distribution
super
would be
small. So
your
you get
guide, but
do a
you
linear
have to
model,
find at
GLM.
least one dimension in which it would be
See
significant.
what you
one
get.
You have to
Random
construct
forest,
this
see what you
feature.
get. Then you deep learn. Then you
Something.
need to do deep learning. Right?
Just
But
Yeah,
you wanna get
all
some
those
features,
techniques doesn't work.
Really? Wow. Even say kind of, you know, clusters of, you know, very fast entering, like, you know,
Those clustering techniques doesn't work.
When you
No,
Anomaly
don't
detection
doesn't work.
I didn't mean clustering, actually.
Doesn't
I meant
mean that
clusters
we
of
cannot find any fraudulent activities, abnormal anomalies.
Is there a parameter?
Just like she's saying,
suppose you use
can
R.
you get close to Gaussian
Then how do you,
distribution?
There's
in R
no,
you
we
have
don't know
put-
what the
features works
distribution
too.
is.
they have put a how does it
No,
work
in
in R?
one
Is
dimension,
there
yeah, you
another
look at
function like
one
that, like
dimension.
D features?
Yes, it's
In
called
the R
deep features,
document,
correct.
Find
It's
the
called
problem.
deep features.
it's already
You
in the
look
R
at one
documentation
dimension,
also.
yeah, anything out of
Can you show
two
that?
standard deviations
Not in the vignette,
outlier.
though, I
But
think you're right.
when you look
It might
at
be
the
only in
second
the-
dimension, suddenly that becomes a normal. Because
R-
in second dimension, you can define another distribution that looks like a normal,
Yeah, see,
but
there's
the
a function
others
called
are
H2O deep
abnormal.
features,
But adding
which
the
takes,
more dimension, those
H2O
becomes
deep
normal.
frame, the
again.
model.
It takes
So
the
that's
data,
the
the model that
problem.
you
So
have
it
built
depends
in,
on how you define
and the layer.
it.
So I can go into
And
my
one
RStudio.
dimension doesn't work. You have to look at every dimension. Find out what
have a
are the
model here,
common
let's see.
pattern in all dimensions and what
haven't
it
built
doesn't
yet.
fit. So that's why deep
okay.
learning
So you need
is
the
trying to
combination
do.
of
You
all
can,
the
I mean, I can just do a
dimensions.
Can you show me the
question.
first few lines where you are
I see.
downloading the package?
So that's why
Okay.
the deep learning
How
is
is this
trying
working?
to do with
Because-
this,
At the CRAN mirror.
auto-associative techniques.
Is this available
You
publicly
reconstruct
or
the same thing.
in the minute? Huh?
But it doesn't.
Yes,
but
exactly.
if
The
you
vignette
you
explains
cannot
exactly how to do this.
construct it, then it
Okay,
becomes
okay.
outlier.
Because this is
It's
unless you have
anomaly,
these
so-
5 lines, you
but
can't
the problem
even.
is that if you
Correct
distribute
If you have a
it,
question, send us
you
to
have a
H2O
huge
stream
data.
if you
You
don't
have
know
to
what's
distribute
going
it in
on.
different
But,
nodes,
yeah, that shouldn't
and
be-
different
shouldn't
nodes
be a
only
problem.
see
I mean,
partial
if you
data.
have an
not
issue,
full
let me
data.
know.
So
You
that's
will
the
you'll probably go down and you'll just add the deep
much
features.
deep features, yes,
and
exactly.
then you
billions
can-
of data, billions of rows.
But we can divide and conquer.
Divide and conquer doesn't help.
This is autoencoder.
Because
this is
you
very
have to
helpful.
see
The more
everything
data,
together.
the high accuracy.
Best thing to start
I mean,
R is easy.
so
with
as
can
you were
H
saying,
itself, right? You know,
go to that
or
model.
among the activation
After a
functions.
certain
Which
number
one should you choose first?
I use rectify because it's faster and I get good numbers.
But for
Really
classification,
if you have binary data,
it is
then what should
true,
you use?
But for anomaly detection,
how-
that's a different
doesn't matter.
story.
I use
It doesn't fit
rectify
in
with
that
Higgs.
level of problem. So that's a whole different problem.
Billion is really not that big.
I'm sorry,
It
can
is,
I ask you also? So Spark uses
So
this
billion
RDT,
rows.
resilient
Billion
distributed
rows.
data sets, and so they have a way to reconstruct the
could have 100,000
lost
dimensions.
objects from its lineage or
Correct.
transformations.
Imagine that each user
So how
have the
do you do
visited
anything?
website in
So
different
that's what I
times.
was trying. How
It's a
do you
different thing,
kind
right?
of
Spark is a
right?
platform that makes
Millions of
HDFS
users,
in
you
memory,
have millions
so to
of,
speak.
Right.
You can plug
Millions
it
of
in,
the
but you don't change it. It's read-only, so to speak. Then you make a new transformation. You add a column or whatever. It's another RDD. Every materialization of your vectors is another RDD, which is read-only.
Okay.
And then you say,
Our
now I need
data
to
is
do
bigger
cosine
than
of
that.
everything. Another RDD, that's cosine of everything, has this lineage, as you say, it has this transformation built in. It knows, once you ask for my number, I need to get the number, I need to add cosine, and then I'm here. Right? It has to do this math. And if it's lost, then it does it again. Yes. And it will get it from disk if needed to restore that cosine of that number.
Okay, so
But you don't
how
change
do,
it, right?
Yeah, how
We
do
are
they
way
do?
faster
How do they?
changing stuff.
How do they then pipeline it? So they don't want to change the initial, data in HDFS.
Yes,
So
they don't.
where do they pipeline the results then?
Nowhere it stays in RAM
and to do something, right? And
to do something. So it's up to you. They don't provide
exactly.
any
So you can do an ML
here.
lib. MLIP has just started, right? It's younger, it doesn't have all these features.
Right, it doesn't have this nice interface.
But it will be native to Scala in their way, and you don't need any extra stuff. Right? The benefit is you just install Spark and you're fine.
But it doesn't work
you don't have
GLM.
anything, right?
I tried GLM, absolutely doesn't work.
Yeah,
what do you
it's
mean?
not ready.
It's not ready.
It's all it's academic, right? It's basically early stuff.
They just trained with the unit tested with the very
small stuff.
Small stuff.
But you can write
real
your own
data.
ML on the top, right? It's up to you. If you write your own ML,
I don't want to spend my time. He's spending a year to writing the algorithm.
Of course.
But it will get there.
So my understanding was that somehow you try to take advantage of each other's code. So if you have this nice interface, although kind of for full kind of
they're gonna use
truth.
Spark,
yeah,
for sure.
But so you have this limited number of knobs. You have beautifully everything designed, but you have still limited number of knobs. So you're adding these knobs.
That's why it's open source, right?
Right.
You don't have to add it. You can add it, right? It's open source. It's just Java. I mean,
okay. So I go through your interface. Can I do through your interface? Do you do something like integrating now with Spark jobs or with ML on Spark, or can I use your knobs and use actually Spark jobs? Or
well, that's all in the making right now, right? Maybe Tom can help you here, our VP of engineering. He will know more about Spark. Because he's asking Irene is asking, what's the future with Spark and HTODEC? How is that going to work together?
Oh yeah, sure.
So because I went, remember to the Meetup where you were talking about
presentation.
Zero garbage collection.
Congratulations. I was very excited about that. See if that how we're gonna do it in the Kaggle.
You have taken the 18
I want to get higher now. I'm 17. I'm like, no.
Exactly, 17. Yeah.
This implementation is really because it's a lot of work. Because see all these these tuning methods that you spoke, you got all of them inside there. Like I mean, so kind of you borrowed.
We have lots of these. See, these are tests here that are running as JUnits over like many nodes, 3 or 5 nodes, and I try with or without replication, with or without load balance, with shuffling or not, with balance or not. Responses, numbers like different responses, like is it binomial, multi-class regression, different data sets. How many points for scoring of the training and validation? Is it a validation data or not? Or is it the same? How many fold?
But that's all
validation.
We've already
how many? Whether you override the best model at the end, whether you keep the consolidation, everything, and then you do run all these combinations.
So this is Scala.
This is Java.
This is Java. Okay.
And then it runs all this stuff, and it tests the web page. There's no assertion error or anything.
An application
it runs a checkpoint restart.
So what we're doing is writing
it looks at the numbers, it compares the results, validation data, AUC, compares that it's exactly the same, computes confusion matrix, everything. Then it does a expression. It
this environment
if this guy is bigger than 0.5, then it becomes a 1, or otherwise will be 0. I made labels
from Spark to H2O
in this expression.
Start with a Spark.
Which is kind of
start with
it's ugly to do this in Java.
Query,
just execute
an
expression.
But you should not hardcode this 0.5 because many times like
correct. That's why I make it again with threshold.
Algorithm,
Threshold is obtained from the model. Make compare whether it actually matches the AUC computation's own threshold.
But everything is there a way to put the threshold in the through the URL? There is a way to do that because in Higgs boson there is a threshold actually. There is like 15% or 20%.
Oh, I see. Interesting. Let me see.
There must be.
The 18th.
I don't know if it's been announced because
there should be a threshold. Should be. If it is not there, it should be there actually.
I don't know.
Should like.
Oh no, for sure. We find that threshold ourselves.
I think is when we're.
targeting to show that. Now, you know, it's very, very real-time engineering, so if it doesn't work, then we might push it out a few days. Or,
so what is there on the 18th? What is there on the 18th?
So the 18th is basically showing the goal is preliminary results.
So now let's look at see the threshold for maximum F1 is 0.36. If you want maximum accuracy, it's 0.5.
But you cannot change the threshold as a this cannot be a parameter in your model.
No, it's not in the model.
Oh,
it's only. This is fixed. The sort order of probabilities is fixed. AOC is fixed. And all you can do is you can move your mouse and see how your confusion matrix will change.
No, but like what I was talking about, like see, you have this is running on the training data, right? This whole ROC curve. You build this whole thing on training data, right?
Sure. The training was on training, but this can be done on validation.
Yeah, it can be done on validation, but when you run on, so here it is currently running on a training data.
What it will do we're using.
No, in this case, it's actually using part 1, part 0. It's trained on part 0, but it's on validation. And now you get the volume is the area is the same, no matter what your threshold is, but your classification into labels
will change based on where you are. Right?
So you can see what it does. So I do default is F1, optimal F1. You can do MCC or whatever.
Yeah, in my case, I have to kind of balance it.
Less false positives.
Yes, less false positives. Yeah. So that would be a kind of I was going to ask you add this feature kind of thing. Like when you have the imbalanced data. So balancing the data is sometimes people do it 50%. Yes. But sometimes I would like to do it like a 25%.
Then you would have to do it yourself now, and then correct the probabilities yourself.
Yes. And then load the data.
If you care about the probabilities,
we do that.
Yes.
Or if you just care about the sort order, then it doesn't matter. But the AOC will be right anyway. And if you correct the probabilities, then your probabilities, the actual probability will be correct.
Yes. So the problem in our production system is that once the threshold become very, very small, like 0.0001, so I have to kind of adjust it. But once I do it with balanced data, so the threshold become more 0.3, 0.2, something like that. So it's more stable, So that's the reason. If you look at the Kaggle problem on the click-through rate prediction, they did the same thing, add the 25% click, which ridiculous, no one get the 25% click,
But I see.
So
even the challenge gives you that data already
in
a balanced way.
Balanced way, they already did. But in
like
practice,
the Higgs also is 50-50.
Yes.
Higgs is quite balanced.
53-47. In reality, it's 1 minus 10 minus 6, right?
Yeah. Exactly.
Or something like that.
You have to kind of do it. But it would be a nice feature, could in the
say what it should be.
Which should be, like I would.
What if you have 400 classes? And if you give me a vector of 400 numbers?
Yes.
That's what.
There's multi-classes example. That plus another good feature. How many samples enough for multiple classes to be statistically significant? These distinguishable.
Yes, I know.
So that also another good feature that I think would be very valuable.
It would not be hard to do, right?
Yes.
Right now it's
And he's really excited because he gets
prior class distribution.
without having to write it himself.
There's a that says this is the real distribution from the data. The model class distribution is the one that you want for modeling. And I say 0.5, 0.5.
Yes.
Or 0.2, 0.2, 0.2, 0.2, 0.2. If you want it to be different, then all you need to do is look at where is this called from. And there's only one caller in deep learning.
Now I'd say that one of those wasn't so stable.
Oh, I see.
Right.
So first it samples it stratified, and that balances it already. And then it says compute my distribution and set that. And now that these ratios are set, they are used for probability correction at the end.
Yes.
But the stratified sampling guy is the guy that already makes it balanced.
Yes.
So these are the sampling ratios per class.
Yep.
And I just compute them to be train sampling factors, which I say is a float of this many. Let's see. Oh, it's new float, so it's all fresh. So I think this guy gets sent filled by this guy. Or maybe this is the output. Array containing the requested sampling ratios per class. Or will be overwritten if it contains all zeros. I see. So if it's all zeros, I'll fill it up. Otherwise, you could give me one. And then I will use what you give me. So already I have that API here. If you filled up, if you put in math here, it says is so and so, then it will just work.
Oh, okay.
It wouldn't be hard, but
that's great.
So and all you need to do is another array here. In the top, literally you would write, you would write something like this. You make an array and say desired whatever, right, ratios, and then you write here